Alright, so a system of equations. A system of equations is what we get when we take multiple equations into account simultaneously. So in this example, this is to solve the system of equations and interpret the solution graphically. Each of these equations individually has their own solution. So x plus y equals 5. This is the solutions to this would be a set of a bunch of points that make that equation true. So 1, 2, 3, 4, 5. Just for graphing this, what I'm doing is I'm saying x plus y equals 5. That's the equation. I'm figuring out what the intercepts are. So if x equals 0, this part kind of gets covered up, then we get the equation y equals 5, because 0 plus y equals 5, thus y equals 5. So this gives me the point 0, 5. That's the one I just found. That's the y-intercept there that I graphed. But similarly, if the y-coordinate is 0, if y equals 0, then we get x plus 0 equals 5. Thus, we get the point 5. Oops, that's not equal to. Thus, we get the point 5, 0. So 1, 2, 3, 4, 5. These are the intercepts of this line. So to graph it, we would draw the line that goes through those 2 points. Let me see if I can do a little better job getting through my points there. There we go. Alright, so there is the line that contains those 2 intercepts. For graphing 3x minus y equals 3, I would do the same sort of thing. If x equals 0, then we get the equation, I'll plug in 0 here, we get 0 minus 3 equals, or 0 minus y equals 3. This negative we'd have to deal with, so we'd get y equals negative 3. We'd essentially have to divide both sides by negative 1 there, because this is the opposite of y. Divide both sides by negative 1, we get the negative comes over here. So that gives us the point 0, negative 3. If, however, the y-coordinate was equal to 0, we'd get 3x minus 0 equals 3. This part goes away. We get 3x equals 3, or x equals 1, because I divide both sides by 1. This gives me the point 1, 0. So 1, 2, 3, 4, 5. The point 0, negative 3 is there. The point 1, 0 is here. So graphing this line looks about like that. Okay, so all I've done here is I've graphed the 2 lines on the same axes. This is the x plus y equals 5, and this is the 3x minus y equals 3. It's a good idea to label these. However, sometimes it can be a little cumbersome to actually write up the full equation on these, so sometimes I like to label them as equation 1 and equation 2. So I'll call that equation 1 and that equation 2. It's just a little easier way to refer to them. In any case, points that satisfy equation 1 are along this line. This point satisfies equation 1, this point satisfies it, this point satisfies it, and so on. Points that satisfy equation 2 are along that line, similarly. So if we're looking at satisfying the system of equations, what it means to satisfy the system of equations is that both of these equations have to be satisfied. So that means we need to find a point or points that make both of those equations true. And what it means for the equation to be true is that it's on the line. So we need to find a point or points that are on both lines. So that point right there is the solution to the system of equations. Now, based on my drawing here, this kind of looks like this might be the point 2, 3. The x-coordinate of 2, y-coordinate of 3. I'm kind of relying on my graph there. I'm not sure that that's right, so let me go ahead and check this. Check the point 2, 3. I'm going to check to see that it satisfies both equations. So with the first equation, that's x plus y equals 5. Well, 2 plus 3 equals 5 is a true statement. So it satisfies the first equation. And with the second equation, 3x minus y equals 3. Let's see, 3 times the x-coordinate minus the y-coordinate equals 3. That's 6 minus 3 equals 3. That's a true statement. What I'm doing here, I probably should do little question marks next to these, because I'm not stating that they're equal. I was checking to see if they were equal. In any case, this point 2, 3 does satisfy both equations. So this is our solution to the system of equations.